Welcome. In this video, we will explore the simple pendulum by plotting log of the period against log of the string length. We will determine the gradient and intercept from our graph and discuss key precautions for accuracy. Let's dive into this fundamental physics experiment. You are provided with a stopwatch, a pendulum bulb, a piece of thread. We are going to replace the split cork with this since we don't have one. A meter rule, and other necessary apparatus. Set up a simple pendulum as shown in the diagram above. So this is the diagram. First of all, we tie the string to the pendulum bulb. And we fix the other end of the string to the retort stand. We just want to press the string against this material to hold it. Adjust the length of the pendulum until L is equal to 90 centimeters. So we are going to adjust the length of the string such that the distance between the base of the material used as the split cork and the middle of the pendulum bulb is 90 centimeters. And that is the length of the string. Give the bulb a small angular displacement and record the time for 20 oscillations. So we are going to pull the bulb to this side, release it and start the stopwatch simultaneously. When the bulb moves to this side and comes back, it will be counted as one oscillation, and on the 20th count we stop the stopwatch and record the time for 20 oscillations. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So we have T1 is equal to 38.13 seconds. And we are going to determine the time for another 20 oscillations and find the average of the two times for accurate results. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. So T2 is equal to 38.06 seconds. So we find the average of the two times. That is time 1 plus time 2 divided by 2. So we have 38.13 plus 38.06 divided by 2, which gives 38.10 seconds. Determine the periodic time T. The period is the time for one oscillation. So we are going to divide the time for 20 oscillations by 20. So that will be T divided by 20. So we have 38.10 divided by 20, which gives 1.905 seconds. And so this is the period. So we have the length here in meters. The length of the string was 90 centimeters. So we change it to meters by dividing it by 100. And we have 0.9 meters. But we leave it in 3 decimal places. That is 0.900. This is time 1 in seconds. For the first trial, we had 38.13 seconds. And for time 2, also in seconds, that is the second trial, we had 38.06 seconds. And this is the mean time T in seconds. That is 38.13 plus 38.06, and the result divided by 2, giving us 38.10 seconds. And this is the period also in seconds. That is the mean time divided by 20. That is 38.10 divided by 20, giving us 1.905. And we are going to repeat the procedure for 4 other values of L equals 80 centimeters, 70 centimeters, 60 centimeters, and 50 centimeters. So we change the length of the string to 80 centimeters. That is 0.8 meters. But we leave it in 3 decimal places. And record the time for 20 oscillations. Record another time for 20 oscillations. Find the mean of the two times and evaluate the period. And we do the same thing for length of 70 centimeters, 60 centimeters, 50 centimeters, and tabulate the results. Given that log T is equal to log K plus N log L, where K and N are constants, plot a graph with log T as the ordinate, that is the vertical axis, and log L as the abscissa, that means the horizontal axis, and hence determine K and N. We are going to plot log T on the vertical axis and log L on the horizontal axis. So we need the values of log T. So this is log of the period, but the period is in seconds. But the log of the period itself doesn't have a unit. This unit, the unit of the period, is put in brackets. The unit is for the period and not the log. So we are finding log of the period, but the period is in seconds. So we find log of 1.905 and is 0.280. We leave it in 3 decimal places. We find log of 1.790 and we have 0.253. Log of 1.675 is 0.224 and log of 1.545 is 0.189 and log of 1.415 will give us 0.151. And we also need the values of log L. So we have log of the length, but the length is in meters. So we have log L in meters, and log L does not have a unit. So the first length is 0.9. So log 0.9 is negative 0.046. Log 0.8 is negative 0.097. Log 0.7 is negative 0.155. Log 0.6 is negative 0.222. Log 0.5 is negative 0.301. The first value on log t axis is 0.280, and plotting 0.280 on the graph is going to be very challenging. So what we will do is that we will change it to standard form. So we'll move this point 1, 2, 3 and record it as 280 times 10 exponent negative 3. So we have log t slash 10 exponent negative 3, meaning 280 times 10 exponent negative 3 will give us the value 0.280. The next value, we move this point 1, 2, 3 and we have 253. So the next one is going to be 224, the next one 189 and the last one 151. For log L axis, the first value is negative 0.046. So again, we move this point, the decimal point 1, 2, 3, and we have negative 46. Also times 10 exponent negative 3, meaning negative 46 times 10 exponent negative 3 will give us negative 0.046. The next value, we move this point 1, 2, 3 to the right and we have negative 97. The next value is negative 155, negative 222 and negative 301. So we are going to plot these values on the graph. The values under log t are all positive, so we use the positive part of the graph. And the values under log L are all negative, so we use the negative part of the graph. We are plotting log t on the vertical axis and log L on the horizontal axis. We choose a scale. We will choose a scale of 2 centimeters is to 20 times 10 exponent negative 3 on log t axis. But looking at the values of log t, we can start from 100 and keep on adding 20. So we have 120, 140, 160 and so on. And on log L axis, we choose a scale of 2 centimeters is to negative 50 times 10 exponent negative 3. But we start from 0. We have negative 50, negative 100, negative 150, and so on. On the vertical axis, each big box is equal to 20, and 20 divided by 10 is equal to 2. So each small box on the vertical axis is equal to 2. And on the horizontal axis, each big box is negative 50. When we divide negative 50 by 10, we have negative 5. So each small box on the horizontal axis is going to be negative 5. This is going to guide us to plot the graph. For the first point, we have 280 on the vertical axis. This is 280. And negative 46 on the horizontal axis. So negative 46, let's count the boxes. We have negative 5, negative 10, negative 15, negative 20, negative 25, negative 30, 35, 40, 45, and 46 will go into the next box a little bit. For the next point, we have 253 on the vertical axis. This is 240. The middle of 240 and 260 will be 250. One box is 2, so 252, and 3 will be in the next box, the middle of the next box. And negative 97, this is negative 100, so negative 97 will be around this place. The next one, we have 224. This is 220, 2 more boxes for the 4. So 222, 224. And negative 155. This is negative 150. So one more box will be negative 155. So the point will be here. And we have 189 on the vertical axis. This is 180. So 180, 2, 4, 6, 8, 9 will be in the middle of the next box. And negative 222, we have 5, 10, 15, 20, and 22 will be in the middle of the next box. 151. The middle of 140 and 160 is 150. So 1 will be in the middle of the next box. That will be 151. And negative 301, this is negative 300. So we go a little bit into the next box and we have negative 301. So the point will be here. So we draw the line of best fit. Now we are going to find the values of n and k from this equation. The slope-intercept form of the equation of a straight line is given by y is equal to mx plus c. That is, when we plot y on the vertical axis, x on the horizontal axis, then m is the slope and c is the intercept on the vertical axis. Comparing the two equations, we are plotting log t against log L. We can rewrite this equation as log t is equal to n log L plus log k, since addition is commutative. So in this case, when we plot log t against log L, log t has become y, log L is now x. So the gradient is going to be n, and the intercept on the vertical axis c is now log k. So from the graph, log k will be the intercept on the vertical axis, which is 300. But don't forget times 10 exponent negative 3, since we converted the values to standard form. And 300 times 10 exponent negative 3 is 0.3. 3. So we take antilog of 0.3 to get k. So the antilog of 0.3 will give us 2.00, and that is k. And now by comparing the two equations, n will be the slope. Since a graph of log t against log L is a straight line with slope of n and intercept on vertical axis as log k. So we are going to find the slope, and that will be our n. So for the slope, we draw these horizontal and vertical lines to make a triangle with the line of best fit. We name here A, name here B, and here C. The slope is change in BC over change in AB. For change in BC, we have, this is 260, the middle will be 270, so 272, 274. So 274 minus 140. Don't forget times 10 exponent negative 3 since we changed them to standard form. And for change in AB, we have negative 50 minus, this will be negative 325 times 10 exponent negative 3. So we cancel out times 10 exponent negative 3. And 274 minus 140 is 134. Negative 50 minus negative 325 is 275. And when we divide, we have n is equal to 0.49. That is the value of n.